Okay, welcome. So I feel like we're missing half the class, even though our class has been slowly shrinking over time. So congratulations to y'all who have survived to quarter 3 now of chemistry. And so I just want to talk about a couple of upcoming things we have on our radar. And also what I learned. So over spring break, I went to a chemistry conference, and that was nice. So I try to get some information about REUs for y'all, so research opportunities, and also not to put Izzy on the spot, but congratulations for, she applied to one of the REU programs that I had mentioned, and she actually got in, so that's awesome. And so if y'all are interested in some opportunities, so I was looking, and so unfortunately, one thing that I learned at the conference is that there's not a lot of in-person networking anymore, and apparently it's just go online and apply for stuff. And so what I was looking at, so NIST was, the National Institute of Standards, was talking about some REUs, but now apparently you just go to USA Jobs, and so a good place for y'all to go, and I can put a link to this, is they have like a student category. And so if you go under that student category, you can find all these different jobs that are like intern positions, looking for recent graduates or people that are currently in school. So that might be a good resource to check out. And the other thing is you want to keep like an eye open on these deadlines. So this is the NIST, so they're the ones that do like all the standards for chemistry, so like the nice tables that we look at. They do the data, and do the research, and I think the application just passed, but you can of course just keep an eye on it for next year if this might be something you're interested in. And so they have 2 different campuses where they do their opportunity, and of course you get paid, but you would just, again, want to keep an eye on that USA Jobs website. And so I think this one has a deadline of February, so again, it kind of passed, but you can keep an eye on it for next year because they'll just keep coming around. And then just keep an eye on the USA Jobs website as well, and you'll never know what internship opportunities come up. So that's my small spiel on research. So look for research opportunities, look for internships, super valuable. And then, so let's take a look at our syllabus to see what we have going on. And so again, since it's the few and the proud now for the Chem 223, we did not make a second lab section, so there just aren't enough people. I don't think they'll give it to us. So if anyone has like a really hard conflict with that, just let me know and we'll try to figure out a resolution. But right now our lab time is for Thursday, so that's our only lab session. Again, I apologize. You can yell at your classmates so that we only had 21 students, so that did not give us enough. But then let's take a look at our lab topics to see what's going on. And so this week we'll have our first lab. So I printed it out for y'all so you can at least look over it. It's kind of math heavy, but then we'll go over it in class as well. So you'll have the pH probes, and hopefully you'll do the hydrochloric acid data yourself. Ideally you'll do the vinegar too, but there's filled in values as well in case you don't get that far. And then ideally you'll do phosphoric acid, but again there's data there just in case you don't make it. So grab a copy of that so you're prepared for lab this week. And then so if we look at weeks 2 and 3, we have this special Earth Day project. And so I at least wanted to talk about that so you can start thinking about your groups and what you might do for a fun topic. So let me hand out. And so the idea is we've given you kind of 2 weeks in lab to kind of play with your topics, and maybe week 2 is like you playing with it, figuring out how this demo is going to work, and then week 3 you can finish up your poster. Of course, you can start your poster presentation as well on week 2. And so we're doing this to present on Earth Day, and so if you're available on Friday, April 21st, you'll get extra credit for presenting your demonstration, and so there'll be an extra 5 points there. And so we'll be inviting, of course, members of the community. So we want to think about kind of interactive kitchen chemistry that would be fun to display. And so we want to think about like a hands-on interactive kind of demonstration. And so these are just some ideas, but of course, you can go crazy. So you could do like some sort of natural pH indicator. You can even think about like having a straw so people could blow into the pH indicator and then it'll change with the amount of CO2. So that could also be like cabbage, or someone brought this up last quarter, like that butterfly PT. That's also pH sensitive. So anything that's natural and changes color and pHs is cool. You could talk about, even recycling. And I have either a silicon bouncy ball demo, or you can make like a glue bouncy ball with borax, but just thinking about like polymerization and how that relates to recycling. There's another, again, like CO2 and acidity. So there's different things for that. There's also like little algae that I'll bring this Thursday, so you could check that out and see if you might want to use that. We also have, I think you might have done this in biology, some of you that are in biology, you have like those little mini veneer CO2 detection chambers, so y'all could come up with some sort of demonstration to show that off for people. And then, any sort of soil composition, composting could also be cool. If you wanted to set up some sort of like compost project, or even just talking about what's in the soil. Water chemistry is also huge if you wanted to talk about, how even the water treatment in Medford works and anything like that. So it's super open, but I want to at least introduce it to you all now so you can think about what your groups might be. So again, you can work in groups of 2 to 3 people and start talking about, what would be fun. And then you'll want to have a poster. And so I'm asking y'all to buy it, but if this is a financial hardship of buying a poster board, just let me know ASAP so I can get some poster boards and bring those in for those who need that. Are there any kind of questions about this? Yeah.
What time would the presentation be about on Earth Day?
So if you can make it, I think Earth Day is from 11 a.m. to 2 p.m. So you just kind of stand out there, and if we don't know who's going to show up, but ideally there'll be groups of people that walk by, and then you can just give like a short 1 to 2 minute spiel. Hey, this is my poster about recycling or whatever, and show your little demo. Yeah.
With talking about like doing like a micro like desalinity project be like in the same realm?
Yeah, as long as you could like make a little project or just some sort of scheme or like why it's important. So that's the main thing, is you ideally want something hands-on or something that they can look at and then explain the importance of it and just relate it. But yeah, it's super open, so I want y'all to have fun with it. Other questions? And then also, as ideas pop into your head, just let me know ASAP so I can coordinate with the stockroom, and either myself or Nicole can buy whatever materials you need. So if you need cabbage or other vegetables or something, just let me know so we can get those materials for you. Awesome. All right, so that'll be weeks 2 and 3. And then we have our regular lab. Week 5 will be our exam, so no lab. And then week 6, putting this on the calendar. So I might have to eliminate this Tuesday date. I just got off the phone with them. But the idea is we want to go visit the Oregon caves. So we used to do this field trip in the past, and we haven't done it with COVID and blah and blah. But we're trying to revive it this year. And so it kind of relates to our solubility chapter more, but I pushed it off to kind of after the exam. And also, since it's been so snowy, the caves haven't even opened. But I had a conversation with them, so it looks like they'd be open to having us that day, Thursday, but we'll kind of talk about that more. We might have to cancel class as well, to give people plenty of time to schlep over there. But that's kind of on the calendar.
Where are the Oregon caves?
They're like in Cave Junction, basically. So like Grants Pass and then keep driving like back south. And y'all can arrange like carpools amongst yourself and all that good sort of thing. And then, so then we'll continue with our regular labs, week 7, week 8, week 9, so this is a fun lab. And then notice, looks like we won't have a chance for a lab practicum, so hopefully you guys aren't too sad about that. But with all the Oregon caves and everything, yeah, I know, everyone's pretty sad. So instead we'll have aspirin, hopefully being our last lab, again, assuming chaos doesn't ensue. Questions?
I don't see soap making on syllabus.
You could do soap making for your project for Earth Day. But yeah, we could still do soap as like a project after extracurricular. I'm totally down for soap making. I know, you've been bugging me about soap, so we should actually do it as a fun project, maybe week 11, as long as y'all bring in your own oils.
Does making ice cream with liquid nitrogen relate to the environment at all?
I like the way you think. I'm sure that you could swing it that way.
Non-dairy, okay.
Yeah, we could talk about that, but I like it.
You could swing it in like a way that like this is how you make extra creamy like non-dairy ice cream.
Yeah.
Throw a vegan like kind of gastrochemistry aspect to it.
Yeah, y'all can stretch it.
Well, my tip for you.
All right, any other questions or anything? Kind of preview of the chapter. All right, so I guess let's dive into our chapter then. So we're doing chapter 21, which is kind of more continuation of acids and more buffers. And so let's dive into it. And then homework is sitting there so you can grab it on your way out. And so the danger of antifreeze. And so each year, thousands of pets and wildlife die from consuming antifreeze. And so most brands of antifreeze contain ethylene glycol. And I think antifreeze can also be in like those little snow globes. They put antifreeze in there. So if those break, right, you would want to keep your pet away from that. And so it's appealing to your pet since it has a sweet taste. And initially, they may have like this drunkenness effect. And so it's metabolized in the liver to glycolic acid. And so this is toxic. So why is it toxic? And so in high enough concentrations in the bloodstream, the glycolic acid overwhelms the buffering ability of our bicarbonate in our blood, so causing the blood pH to drop. So of course that is not good. And so the low blood pH then compromises the blood's ability to carry O2. And so one treatment is to give the patient ethyl alcohol, which has a higher affinity for the enzyme that catalyzes the metabolism of ethylene glycol. And so now we're going to look more into buffer solutions. And so buffer solutions are just any solution that resists changes in pH when either an acid or base is added to the solution. I think we touched on buffers last time. And so If you kind of recall from 222, we said that our buffer solutions must either contain significant amounts of weak acids, and then so if you have the weak acid, you have to have its conjugate base, and so that would be some sort of salt. And so some examples, so we looked at like acetic acid, so this would be vinegar, and then we have to pair it with its conjugate base. So I just picked sodium acetate, but some sort of acetate salt. Or we could have a significant amount of our weak base, and so probably a weak base could be ammonia, and then we would need its conjugate acid salt, so some sort of, ammonium chloride or other appropriate conjugate acid salt. And it's like we mentioned, so blood, of course, is a buffer system we're familiar with. We know that blood has to be kept at a very specific pH for all our wonderful biological reactions to occur. And so blood has a mixture of this carbonic acid and our bicarbonate ion in solution. And so to make an acidic buffer solution, so like we said, we have to pick our appropriate acid. So in this case, if we pick acetic acid, then we have to pair it with our appropriate conjugate base. And again, any acetate salt would work. So potassium acetate, cesium acetate, could go on and on. And so usually the conjugate base is added as a solution as a salt. And so again, we have sodium acetate as the source of our conjugate base acetate ion. And of course, the idea with our buffer solution is, so what happens to a buffer solution when a small amount of strong base is added? So if we add a strong base then to our buffer solution, the added base will be neutralized by the acid component. So then you could write this out as your initial neutralization reaction. So sodium hydroxide plus our acetic acid here, of course, gives us water and then sodium acetate. And the pH of the buffer will change a little bit or slightly increase or not at all. And of course, what we find once we do this neutralization reaction, right, then we know that our conjugate base, our acetate, might go ahead and reform our acid. Oops. So then it reforms our acetic acid, and of course leaves us with a bit of base. And so then what happens to a buffer solution when a small amount of strong acid is added? And so now looking at that reaction, right, the acid would be neutralized then by our base component in this case. So then we do our neutralization reaction, so that gives us sodium chloride, and then back to our acetic acid. So of course that's just our HA in solution. So once again, right, your pH should change a little bit, so maybe slightly decrease if you're adding a strong acid, or not that much. And so if your amount of HCl is less than the amount of our base present, so in this case our sodium acetate, the pH change is small. And so obviously, right, you can overwhelm a buffer solution if you dump in large amounts of acid and it can't neutralize it. And so all of this is, of course, related to Le Chatelet's principle. And so looking at this, so again, thinking about our acidic buffer solution, so we made it with acetic acid, so addition of base to our acidic buffer solution. So our buffer solution contains significant amount of weak acid molecules. And again, our weak acid molecules react with the base and neutralize it, creating our conjugate base and water. and then addition of acid to our acidic buffer. So then again, your acidic buffer solution contains your conjugate base, and it can react with the acid, neutralize it to form more HA, and then of course your equilibrium can be reestablished. And so after your equilibrium shifts, the concentration of H3O plus is essentially kept constant or changes very slightly. So then we can look at our common ion effect. So again, we're looking at kind of the same scenario. So we can think about our acetic acid plus water, and of course is in equilibrium to dissociate to make our conjugate base, and then plus acid. And so we can add a salt then. So they just have a generic NaA, but this could be, right, again, our sodium acetate that contains our conjugate base of the weak acid. And so then if we add our salt, right, so we add this part, so now it kind of shifts it to the left, so thinking back to Le Chatelier's principle. And so again, it's just going to go in equilibrium to try to reestablish that equilibrium. And of course, this salt has to have the common ion. And again, we'll emphasize, so i.e. potentially acetate as the example we're currently looking at. So it could also be like fluoride if we were looking at like a HF solution. And so our A minus, or in this case the acetate, is common to both the salt and of course the weak acid. So those are your generic A anion. And so that means the addition of our common ion, aka our base and our acetate, causes the pH to be higher than the pH of the original weak acid solution due to the lowering of our H plus ion. So going back to this Le Chatelier's principle, if we add more of our base, so we add this, that causes to shift to the left, again away from this H plus. And so let's zoom in and look at it. And so again, you get to play with a pH probe on Thursday. But if we have, so we have a 0.1 molar solution of just acetic acid now. And so that has a pretty low pH of 2.9, at least from our pH meter. And then if we compare that to, so now we're just looking at the conjugate base salt, so sodium acetate, same strength, so 0.1 molar solution. And so that has a pH of 8.9. It's very basic. And then if we combine equal amounts, so 0.1 molar solution of acetic acid and a 0.1 molar solution of our sodium acetate, then we kind of get something roughly in the middle of about 4.7 for our pH. And we'll look at more on how to calculate this in a second. All right, so let's try this. So calculate the pH of a buffer solution that is 0.1 molar in our acid and 0.1 molar in our base. And you'll want the pKa. So the pKa for acetic acid is 4.74, or I'll also give you the Ka. So 1.82 times 10 to the negative fifth. So just take a minute or two and see if you could figure out how to maybe set this up, especially, given what we talked about last quarter with our rice tables. So at least see if we can set up some initial conditions, and then we'll go through it together here. And then I see you in the chat too, so just ask questions or feel free to jump in. So did we at least get to this point? So this is just kind of setting up our initial conditions. So this is just our buffer reaction, right? So we have our weak acid plus water, and then we know if it's a weak acid, it's going to end up forming our hydronium. So of course this donates to our water over here to form H3O+, or you could just of course write H+ colloquially, can't pronounce that word today. And then of course that forms, right, our conjugate base over here. And then this is just our initial conditions, right? So we haven't looked at the dissociation yet, so we don't know, right, how much H3O+ we have. So this is just initially, right, we have 0.1 molar solution of our acid, and then our 0.1 molar solution of our base. So then from there, we can set up our change. And so since we have no, right, H+ in solution initially, we know we're going to have to form something. We don't know how much is going to dissociate, but we'll go with plus X. And of course, this means if this is plus X, this will be minus X. And then our conjugate base will also be plus X there. And so now this gives us our equilibrium conditions. So 0.1 minus X plus X, and then 0.1 plus X. So does this feel vaguely familiar? I feel like should kind of feel like a refresher of last quarter. And so now from here, it's just the fun algebra part. And we might be able to make some assumptions. So let's just set up. So Ka is, of course, just equal to, I'm just writing our generic expression. So acid times conjugate base over our HA concentration. And I gave you the Ka, so of course this is equal to our Ka. So 1.82 times 10 to the negative fifth. So now we can plug in our values. So it's equal to X times 0.1 plus X over 0.1 minus X. And so what can we do from here?
I might be thinking of the wrong thing. Can you drop the lower X since it's a small number?
Yes, exactly. So here's our hint. It's times 10 to the negative fifth, so that's pretty small. So we can just go ahead and actually drop both of those. So then we have, so again, assume x is small, so less than 5%. We'll have to check our assumption later. And then we just have x, then times 0.1 divided by 0.1 is equal to this expression. And of course, if you guys have fancy calculators and want to just plug that in, you're more than welcome to. But again, I do not expect you to do that, so dropping the x is fine. And that divides, and so that just leaves us with x is equal to 1.82 times 10 to the negative fifth. And so then we want to plug this in for x to get our pH. So our pH is equal to our negative log of x. So what's our pH? So I hear 4.74, and so I'll just type that in so everyone can see. Make sure you do it yourself so you know you're in the correct base and all that good stuff. So 4.74 should be our pH. And then, do y'all remember the Henderson-Hasselbalch equation? I think we introduced it last quarter. We're going to bring it up again. We should, so I forgot to check our assumption, but we can of course check that. So 1.82 times 10 to the negative fifth divided by 0.1. So that should be less than 5%, which it looks like it is, but again, I'll just punch it in to be sure. So times 100. So yes, that's only 0.012. Or yeah, 0.02% roughly, so that's way small, so it's fine to make that assumption. And then, so do we remember Henderson-Hasselbalch, or should I give it to you? All right. Oh, we just divided by the, so we just took x divided by the 0.1, since we said that's what we eliminated it from, and then that gave us less than 5%. So that was about 0.02%. So that was good. And so kind of the other part of this is this Rice table is the most accurate way to do the pH. But we can also use our Henderson-Hasselbalch, so let's do that. And I'll remind you of what that equation is. If I can spell it. So this was the equation that you might see two forms of. So the form that I like is pH is equal to your pKa plus the log and base over acid. So if you see a minus form, then it's probably minus the log of acid over base. But for my sanity, I just like using this one, so I always remember base over acid, and it's a nice plus sign. And so all that means is, right, you'll take your pKa plus your log, so then your base is going to be your conjugate base, so A minus, over HA. And so if we go back to our initial conditions, so we had started off with 0.1 molar of acid, 0.1 molar of our conjugate base. So So then we could plug that in, so equals pKa plus log of 0.1 over 0.1. And so if you do the log of 1, that just gives you 0. So that cancels out. And so this just leaves you with your pKa as your answer. And so your pKa of acetic acid is 4.74, which is what we got through our Rice table method. And so this is usually the strongest way to make your buffer too, is equal amounts of base and acid like that. And of course, again, gives you just the pKa for your pH. So here's our Henderson-Hasselbalch equation again. So I would write it down, star it, whatever, since it'll keep coming up. And so it is the relationship derived from our Ka expression of our weak acid solution. And so this just gives us another method to calculate the pH of a buffer solution. It's a lot simpler too than doing all the Rice table. So it's usually much easier for students to plug this formula in. And so our equation calculates the pH of a buffer from the pKa and initial concentrations of the weak acid and salt, as long as the X's small approximation is valid. So that's kind of the downfall of the Henderson-Hasselbalch, but you know, with a lot of these equations that we use regularly, we see that the pKa is pretty small, that we can make that assumption. So as long as you can make this assumption, you can go ahead and use Henderson-Hasselbalch. And so let's at least look at the derivation of Henderson-Hasselbalch. So of course we have our expression, of course, for our generic acidic buffer. And so we're given our expression, so just our Ka is our H plus ion concentration times our conjugate base over the not disassociated HA. Then this is just rearranged. So rearranged to give us our H plus concentration is equal to Ka times HA over A minus, so that's just algebra to get to there. Then once we get to there, we can take the log of both sides, and of course, right, the negative log of this is going to be equal to our pH, and then we'll take the log of this side, so negative log of Ka times our HA over A minus. And so this simplifies to this expression. So negative log of H plus is equal to the negative log of Ka minus our log of HA over A minus. So now we're here. And so then, once you're at this expression, you can rearrange, so multiply both sides by -1, and then negative log of H plus is just equal to pH is equal to pKa, so the negative log of Ka is just pKa, that's just a definition. So this is pH, this is pKa, and then that leaves us with the last little bit plus the log of our base over our acid. So that's how we got to that expression. So you don't need to know how to do this derivation, just appreciate it. That's where it came from. And so now, well, how do we know when to use ice, or when do we use Henderson-Hasselbalch? So of course our ice, or I like Rice. So our Rice method can always be used. So if you're ever unsure, you can always set up the ice method, and this will always work. And again, we can use our Henderson-Hasselbalch when the X is small approximation is applicable. And so it's usually true when the initial concentrations of acid and salt are not very dilute, and the Ka is fairly small, so we see that scenario a lot. And so this means that the initial acid and salt concentrations should be about 100 to 1,000 times larger than the value of Ka. So that helps you kind of judge it so you know whether you're in that, again, 5%. So it has to be less than 5% for that approximation to be valid. All right, so let's see if we can do this next one. So calculate the pH of a buffer solution that is 0.05 molar in benzoic acid and 0.15 molar in sodium benzoate, and it gives you the Ka of benzoic acid. And so I would kind of encourage you to try both methods. Maybe set it up by rice, see if you could take an approximation, compare that to your Henderson-Hasselbalch. So I'll give everyone a few minutes to kind of play with it initially, and then we'll see how it turned out. So if we set it up, at least using our rice method, so we should have gotten something that looked like this. And then once we plug it into our KA, and so what do you notice about your KA expression? So it's small, and so what does that tell you about your X probably? So given how small this is, that means our X is small, so we can probably go ahead and make our assumptions to make the math easier for us. So then once you're here, again, assume X is less than 5%. So now we're just given this expression. And so now we just have to do some algebra. And 6.5 times 10 to the negative fifth divided by 3. So do we get X is 2.16 times 10 to the negative fifth? And so at this point, we could double check our assumptions. So this is our smaller number, so let's see if that was appropriate. So divided by 0.05 times 100. And so yeah, that was about 0.04%. So 0.04%, so that's good. And then, so let's go ahead and figure out the pH then. So pH is our negative log of X from our assumption. So what do we get for the pH by this method? So do we all get like 4.67 roughly or so? Okay, see lots of nods. And then did we get a chance to plug it into Henderson-Hasselbalch?
When I plugged it into Henderson-Hasselbalch, I got 4.66.
So 4.66 if we plugged it in. So go ahead, if you didn't plug it in yet, let's compare that. So go ahead. And of course, for the future on your exam, you know, if you just see this, okay, I see this is a small number, then you can just go ahead and use Henderson-Hasselbalch. And so let's see and verify. So you said we got 4.66. Let's see. Did they give us, they didn't give us a pKa. But we could take this number, put it back into pKa. So just take the negative log of our Ka. Oops, oh my goodness, I'm in a mess here. So then we get about this number for our pKa. You might have a different number if you just ask Google, you know, rounding. I expect small errors in rounding. So then we have about 4.19 plus the log. And so which one's our base again? What's the number for the base?
0.15.
So 0.15. So excellent. So just make sure you're plugging in the right numbers. So that's our sodium benzoate over our acid. So divided by 0.05. And so we get about that plus our pKa. And so yes, I get your number that you got, Vaughn. So 4.66 roughly, 4.67 with some rounding. So it kind of depends. So very close, very same. And again, you know, with rounding, You might have slightly different numbers, but it should be somewhere around there. So that's pretty good. So that tells us that, again, our assumption was good, and so our Henderson-Hasselbalch would be appropriate for this situation. So let's do that one more time for good practice. So now we're looking at the pH of a buffer solution that is 0.25 molar, and our hydrocyanic acid and 0.17 molar, and our potassium cyanide, and it gives you our Ka, so 4.9 times 10 to the negative 10, and also our pKa of 9.31. And so go ahead and use the equilibrium approach, but of course I think y'all are starting to catch on that you see that tiny number, and it's probably appropriate to make that assumption and use Henderson-Hasselbalch. But go ahead and show that they would give similar results. So I'll give you guys 5 minutes or so to get started again. I'll start comparing and seeing where y'all are at. So just touching base with y'all. So again, hopefully it's starting to feel really repetitive and really familiar to y'all. So we have our equilibrium expression, and then set this equal to our Ka once again. And I'll write it generically first. And of course, we'll plug in then our equilibrium expression. So x 0.17 plus x and 0.25 minus x. And so once again, at this point, you probably recognize, well, we're at 10 to the negative 10, so we can probably assume that x is tiny. And so that brings us to x times 0.17 divided by 0.25 is equal to 4.9 times 10 to the negative 10. So what do people get for x once you solve it?
I got 914.
Is that the pH?
Yes.
Or? And so what did you get for x then?
7.2 times 10 to the negative 10.
That sounds good. So I see nods. So excellent. So once you got x, plug that, of course, into our negative log of x to get our pH. And so what did y'all discover when you did the Henderson-Hasselbalch equation? So I heard it was the same. And so let's just run through that really quick. So it's just pKa plus log of base over acid. Let's see, they gave us a pKa. Of course, we could calculate it. But plus our log. And then which one's our base again? What number's the base?
0.17.
So 0.17, excellent. Over the acid. So 9.31 plus my log of 0.17. Oops, I could type. And so, yep, I got the same number that y'all told me, so 9.14.
So to do our check on the 5% assumption, we would take the 4.9 times 10 to the negative 10 and divide it by which of those numbers?
No, you want to take the x value, so whatever you find for x divided by the smallest one. So in this case, by the 0.17.
They were both really small, so it didn't really matter in this instance, but I feel like
Yeah, so anytime, since we eliminated from both of them, you'd want to check it from the smallest, yeah. But of course, what do we say for x? Oh, 7.2 times 10 to the negative 10 divided by 0.17 will still be silly tiny. So 4.23 times 10 to the negative 7%. So assumption, okay. Excellent. Any other questions on that so far? So now let's try some more steps. We'll see how far we get before we run out of time. And so now it's saying use the Henderson-Hasselbalch equation to calculate the pH of a buffer solution that is 0.5 molar in ammonia and 0.2 molar in ammonium chloride. And it tells us for ammonia, the pKb is 4.75. So before I let y'all loose, we might need some help. So do you guys remember the relationship between pKa and pKb? So there's two different relationships that we could use. So this goes back to our water constant. So if you have your Ka times your KB. That should always be equal to that KW water product constant. And so KW, which we always assume that we're at 25 degrees Celsius and blah, blah, blah. And so that's just going to be 1 times 10 to the negative 14. The other relationship, excuse me, that we can use is pKa plus pKb is equal to 14. So similar to how our pH scale works, our pKa-pKb relationship is similar. And so even though they gave us pKb here, we'll want to solve for the pKa to plug it into our Henderson-Hasselbalch. So it's just telling us to use Henderson-Hasselbalch. And so let's see if y'all can do that. So wait on the second half. We'll go through that, what we're supposed to do. But see now if you can use your Henderson-Hasselbalch equation, and given this relationship of pKb, find your pKa, plug in your appropriate base over acid, and see if you can figure out the pH. So take a few minutes to try that. So what numbers did we plug in? So what was the pKa that we found? 9.2, is there another? 9.25. So we have 9.25 plus my log, and then which one's my base? So 0.5, so excellent, since that's ammonia, we know that's our base, divided by our acid, so ammonium chloride. And so did we get like 9.65 for the pH? Excellent. Now let's see, so how would we approach this next problem? So now let's look at what they're saying. So now it wants us to calculate the pH of a 1 liter solution of our buffer if 0.01 moles of solid sodium hydroxide were added to the initial buffer solution. So what might we have to do? What
You have to convert it to
or molarity, or maybe convert the moles, the molarity to moles. And then what is our sodium hydroxide reacting with? So let's maybe even just write that out. So now let's do our second part. So add 0.01 moles of NaOH to 1 liter of our buffer. And so we could just start by writing what is just the reaction before we start trying to figure out amounts and everything. So we're going to have sodium hydroxide, and then who will it react with? What species? So it'll react with our ammonium chloride. And then what is it going to go ahead and make? So it makes our salt, so sodium chloride. Plus our, then I'll reform, right, ammonia, because I'll make that NH4OH, which is the same thing as ammonia. And so now we have to figure out amount. So if it's a 1 liter solution, how many moles do we have just initially of our sodium hydroxide? So how many moles do we say we added? So 0.10 moles. And then how many moles of ammonium chloride do we have? We have to look back. So we have a 0.2 molar solution and 1 liter. How many? So 0.2 moles. So 0.2 moles. And then we need to do our reaction. And so, of course, this will eliminate. And so how many moles of ammonium are we left with then? So you just subtract, since they're neutralizing, so you have a reactant or 1-to-1 mole ratio. What did you say? So 0.19 moles of our ammonium chloride is left. And then what do we make though? So how many moles? So we don't really care about the sodium chloride, right? It's just the salt. But then how many moles of ammonia do we make? So how many moles of ammonia do we make from this reaction? So it's just stoichiometry, right? If this, we consume this amount of sodium hydroxide, so then how many moles of ammonia do we make? What did you say, 0.01? So 0.01 moles. But then, how many do we have initially of ammonia? So we didn't put that in. So how many moles did our original solution contain? So we have 1 liter, 0.5 molar solution. So how many moles do we have initially of ammonia? So 0.5, so I'll just put this over here. So this is our initial condition, so 0.5. Then we kind of did our change. I'll just do change plus equilibrium. So, right, we have no more sodium hydroxide by the end of our reaction. We said we have 0.19 moles of ammonia. And then, so we created 0.01 moles of ammonia, but then we also have to account for the initial amount. So we have to add the moles, so plus 0.5 moles. And so now that we're here, and let's just kind of rewrite it. So by the end of our reactions, we had 0.19 moles of our ammonia, so our acid species, and then this gives us 0.51 moles now of our base. And so from here, if they want to know the pH, we can just go ahead and use our Henderson-Hasselbalch once again, except our numbers will be slightly different. So pKa plus log of base over acid. And so we said before the pK was 9.25 plus, now our new number for our base, so is 0.51. So now that's our base that was created from our reaction over our new acid, so whatever remains after being consumed. And so let's see how the pH compares. And so I get a new pH of 9.67 or 68, I guess, with rounding. I see some nods. So 9.68 for our new pH. And so now this kind of gives us a sense of our buffering capacity. So we said we had a pH of 9.65 initially. Then we added our strong base to it. But of course, with our buffer, it only increased, 0.03 pH points to 9.68. So that's pretty cool there. Any questions about this part? Yeah. How to get the pKa from what? Sorry. So probably the easiest would be to use this 14 relationship. And so all you do, so 14 minus 4.75. And so that's how we got the pKa of 9.25. And then you could also use, so if they had given you just the Kb, then you could take the 1 times 10 to the negative 14 divided by Kb to get Ka. So either one of these would work, just kind of depending what you're given.
So I might have missed it. How can you tell which one's the acid and which one's the base again?
So an acid, just think back to like generally last quarter, acid is anything that makes H plus in solution. Base is anything that makes hydroxide. And so that's where you have to kind of draw out your equilibrium. And so this one was kind of weird. So we have to remind ourselves, right, ammonia plus water. And so that's a base, right? Ammonia is a base, and so form your conjugate acid plus hydroxide. And so it plucked off the H, forms hydroxide, so you know that ammonia is a base in this case. And then if we go the opposite, ammonia plus water, well, that one forms H3O plus in solution, since the water takes one of those H's, but then, of course, we reform ammonia. Other questions about this? So we'll go ahead and stop here for today. I think we're out of time. But then we'll just continue looking at more buffers and probably practicing a little bit more math for this chapter. So don't forget to grab homework. Oh, and then one more thing. So we're going to have a little like pre-quiz. So there'll be a quiz on Thursday. And I'm calling it a pre-quiz because it should just be a refresher of kind of last quarter's material, PKA and all that good stuff that we touched on. So grab homework on the way out. Remember, no lab today, so I'll see everybody else for a lab on Thursday. And see you all on Thursday. All right, thanks for joining on stream. I'll hang around for another minute or so on stream, and then I'll end it. So thank y'all again.
For me, taking the final early, I leave June 4th, the early starts, and then we'll take a break then. Oh, what, we end like 1:13. I don't really know anything. But, for me, taking the final early, would you have office hours, right?
Yeah.
Could I visit you during office hours if I can do it around my work schedule?
Yeah, we can figure it out.
Because I don't want them to like jump into the car while I have to shoot before I leave.
Yeah. Yeah, we could do that. We could meet. I'm pretty free this quarter, so we can meet like on Tuesdays too, or like,
Like, could I say Tuesday after class?
yeah.
Because I work in the morning or the afternoon, 5 to 6, whenever class starts.
Yeah, I'm also free like any of the other days, and we could just set up a time to meet and go over stuff. But yeah, I definitely want to work with you. That's awesome that you got into the REU. So it's like, yeah.
I was just like, no way. I didn't think I would get it.
No, I'm like so happy for you. Like it's an awesome opportunity. Like,
So they gave me the plasma material.
oh, cool.
So I'm like, I don't know anything about that, but we're gonna make it work.
Yeah, I mean that's what it's about. So super awesome.
I just want to let you know that I won't be in person on Thursday. I'm going, there's a con up in Portland I'm going to this weekend, and I'm going to be taking the Amtrak up Thursday, so I'll be on class in a train.
Okay, yeah, and then you'll probably either have to make up the lab like
Right, the lab.
online or, yeah, we might do it in person too. But I think for that one, all the materials are online.
Yeah,
So I don't know if that's easier for you.
probably, yeah. I definitely got behind last quarter, and it definitely really hurt my grade because I was testing really well, and then everything else not so well.
Yeah, so you just gotta keep up trying to stuff.
Yeah. And I still have not written the draft of my essay. I will try to get that done in the next 2-3 weeks and submit it for review.
Yeah, that sounds like a good plan. Because sooner you give it to me, the sooner I can give it back to you.
Yeah, definitely. I should have been working on it during spring break, but I just didn't.
That's okay. It happens.
Yeah. Well, that's the plan. I will try to. I'll be on campus tomorrow, and I'll only have trigs, so I'll probably just stay after and get the lab done online. And all the materials should be online, all the data and stuff.
Yeah, I might have to open some folders, but I can do
Okay,
that
sounds
for
good.
you. Yeah.
That would be awesome. All right.
All right. Sounds good. How's it going?
Good. I was just, my classes are overlapping again.
Okay, you're doing the same thing.
Yeah.
Yeah, I just talked about a few things. So lectures on. Oh, I should stop streaming. And then, yeah, the homework. I handed out the lab early just so people could have it. We only have one Thursday lab.
Oh, that's it? Okay.
Yeah, so no Tuesday lab. But then I also handed out this Earth Day project so you could start thinking about it.
Okay.
Just trying to think of like some cool hands-on thing that you could present potentially on. You don't have to present it on Earth Day. It's like Friday, 11 and 2, but
Okay.
otherwise we'll make like a poster. And so like a project. Either a group of 2 or 3 people total. So I wanted to hand it to you early so you can start start thinking about like what fun projects you might want to do.
Okay. Cool. Look at that. Give my son a ski spot. That's his birthday.
Ah, nice, yeah,
Yeah.
that'd be fun.
That'd be a cool
But,
project.
Yeah, you should definitely buy him everything.
All right.
Grab him in.
That'd be cool.
Yeah. All
Thank
right.
you.
See ya.
See ya. Oh, and then we still have the quizzes on Friday or on Thursdays?
Yeah,
Okay.
and so we'll actually do a pre-quiz this week.
Okay.
It should be over like last quarter's material,
Okay.
kind of a refresher quiz, get everybody.
Get the
Everybody
fireworks
brains.
out.
Yeah.
All right, cool.
Sweet. Did y'all grab homework and everything?
Yes. Are you cool with me just continuing to do it online through Blackboard?
Oh, the homework?
Yeah.
Yeah, yeah.
Okay.
Homework is easy to grade online.
It's just easy because then I have it like all in one place to reference back
Yeah.
on paper. Ooh. Oh, data tables.
Yeah. We'll see how lab goes too.
It's gonna be